Hello and welcome to video Waves.3a, wave energy, intensity, and sound levels. In this video, we will be discussing more properties of sound waves to get a better understanding of how our perceptions of sound are different than what is actually happening with the sound wave. Let's go over a few characteristics of sound first to make sure that when we're talking about some words, we're talking about the same thing. First of all, the loudness. Loudness is related to the intensity of the sound wave, but it is partly subjective to the listener as well. So there's a science behind it, but there's also a subjectivity to it. When we're talking about pitch, we're basically talking about the frequency. For humans, the audible range is the range in which we can hear sounds. As we age, our range decreases, typically from the upper end of the range, so we won't be able to hear as many things at the higher frequencies. Depending on what you do for a living and how much exposure you have to, say, heavy machinery, then oftentimes you will lose the bottom end of your range as well. The human range, the audible range for humans, is from 20 hertz up to about 20,000 hertz. Now, other animals can hear outside of this range. For example, dogs can hear higher than 20,000 hertz, as can dolphins. The lower than 20 hertz range is typically not heard by other animals, but it can be felt by them. And the lower than 20 hertz is where you have waves of earthquakes. Ultrasound is also referred to as ultrasonic, and the ultrasonic is where you're talking about frequencies that are above 20,000 hertz. Now remember, when we're talking about ultrasound, we are not talking about supersonic speeds. We are talking about the frequency of the wave being above our audible range. An example of this is if you have a camera and you are having it focus on a person so that, like you set a timer and then you autofocus so that you can get into the picture. The autofocus is done by ultrasonic waves. So the camera sends out an ultrasonic pulse and it goes towards the person. When it reflects off the person, it will come back to the camera, and the time it takes to do that will tell the camera how far away the person is and then be able to focus on it like that. Now, at the other end of the spectrum, we have infrasonic, and infrasonic is frequencies less than 20 hertz. An example of infrasonic are the waves formed by earthquakes, as I said, also waves formed by large machinery. For example, a jet engine's vibrations. Yes, we can hear it, but the vibrations are also quite low frequency. And the problem with infrasonic waves is that they can be dangerous to the human body because they make organs resonate. And if the organs begin to resonate and shake around larger and larger amplitudes, then you can damage the organs, and in extreme cases, you can actually die from it. The last characteristic of sound that we want to talk about is its speed. We know that the speed of sound is about 343 meters per second at room temperature. However, that changes depending on the temperature. So I wanted to remind you that speed is dependent on the temperature, and the equation that relates the two is that the speed of sound is approximately 331 plus 0.6 t. And this, of course, would give you units of meters per second. Now, the T is temperature, and it is measured in degrees Celsius. So if your temperature is 0 degrees Celsius, then we say that the speed of sound is approximately 331 meters per second. What I want to start with, now that we have these characteristics out of the way, is energy. How is energy transported by the wave? What does that mean? And what does it tell us? The energy is transported by a wave through each particle of the medium, so the energy is related to how much the particles are moving. In other words, they must be related to the wave's amplitude. And in fact, it turns out that energy is proportional to the square of the amplitude of a wave. So when we look at sound waves and we want to know how much energy there is, a quick way to tell if it's got a small amount or a large amount is to look at its amplitude compared to other waves. And then the energy is proportional to the amplitude squared. I'm not going to derive that equation for you or an equation out of that for you. It is done in your book, however, so you can take a look at it and see how we come up with that if you are interested. Intensity is the rate of energy passing through a unit area. So as it says here, I for intensity is the energy per time, that's our rate, per area that we are looking at. Well, keep in mind that energy per time is actually equal to power. The rate of energy consumption or energy usage is power. So intensity is essentially power per area. The units for intensity are watts per square meter. But now let's think about this for a minute. If energy is proportional to amplitude squared and intensity is proportional to energy, assuming that the time and the area stay the same, then that means that the intensity of a wave is also proportional to the amplitude squared. So now we have a way of not only getting an understanding of how much energy a sound wave is transporting, but we also get an understanding of the intensity. And remember, just a minute ago, I was talking about how loudness is related to intensity. So our intensity or our loudness is related to the amplitude of the wave. Let's say for a minute that a wave is completely free of obstacles, and if we have a source in the center of space, like over here, and we allow the sound to be emitted and transmitted through the air, it would spread out three-dimensionally from its source. And if the medium is uniform, then the wave itself is actually spherical, not just going straight in one direction as we've been thinking about before. We are talking about a spherical wave being produced by a sound source, and we know that intensity is power per area. The area that we would be going through, well, the volume is a sphere. When we're looking at just one particular section of a sphere and we want to see how much the rate of the sound of the wave going through that section, that then is a circle. So then the intensity really is power over 4 pi r squared. If we assume that the power of the source is constant, then this tells us that intensity is proportional to 1 over r squared if the power of the source is constant. So let's look at this picture here again for a second. If we take a look at this and we think about, all right, the wave has traveled to some distance r1, and then we're going to compare that to the wave when it travels to R2. We're going to compare the intensities at those two places. Well, at R1, we know that it would have an intensity that we'll call I1, and at R2, we know that it will have an intensity of I2. Let's also make the assumption that R2 is equal to twice R1. So you go twice as far when you get to R2. If these two situations are true, and we just said that intensity is proportional to 1 over r squared, then as you double the distance, the intensity gets cut by a quarter. So as r goes to 2r, or r gets doubled, intensity goes to a quarter of the original intensity. So in other words, all of that I'm trying to say here is that sound gets quieter as we go farther away. Okay, so let's put all this stuff together that we've been talking about in terms of waves and in the intensity and the energy and figure out what we all have going on here. So to wrap this up, we have said that intensity is proportional to the amplitude squared of the wave. We have also said that intensity is proportional to 1 over r squared, the distance from the source. Well, if you combine these two, and if I is proportional to each of them, then they are proportional to each other. So if a squared is proportional to 1 over r squared, then a is proportional to 1 over r. So remember that intensity is related to loudness of the sound, and it is measured in watts per square meter. Amplitude, remember, is measured in some form of meters, as is the radius. So again, the amplitude decreases as the radius increases, is what this is saying. Going back to the same thing that we said a minute ago, that the loudness of the sound decreases as you get farther away. Now, the human ear can hear a range of intensities just like it can hear a range of frequencies. So when we talk about the intensities that it can hear, the ear can hear intensities from about 10 to the negative 12 watts per square meter up to 1 watt per square meter. Now, this is a huge range, 10 to the negative 12th to 1. That's enormous. But the reason that the range is so large, and we don't really think of human ears and human hearing as being the most phenomenal hearing out there, because there's a lot that we really can't hear, there must be something else going on. And that something else that's going on is that intensity is not a linear scale to our ears. So as the intensity increases or decreases, it doesn't mean that things get twice as loud if you double the intensity, or if they get a quarter of the loudness if you cut the intensity in a quarter. In fact, intensity is actually a logarithmic scale, so twice as loud does not mean that you have twice the intensity. In fact, twice as loud means that you have 10 times the intensity. Let's put this into some terms that you can understand and that we can think about in terms of things that we listen to and we hear in our lives. When we are talking about the intensity of sounds, we often do not, in fact, use the watts per square meter units to talk about intensity. Instead, we've created another scale that's easier for us to understand, that is relative to things that we hear in life, and its measurement is called the decibel. Deci, as in the prefix deci in the metric system, and bells named after Alexander Graham Bell. So decibels is what we're talking about. And if we measure the perceived sound levels, we do so in decibels. And let's just take a look at this chart for a second. We can see that we have down here at 0 decibels, the threshold of hearing. This is equivalent to the intensity, the smallest intensity that we can hear. We can't hear anything that has an intensity smaller than this. And then we go all the way up to 120 decibels, which is the 1 watts per square meter. And 120 decibels is what we call the threshold of pain. What this means is that it physically hurts for you to hear sounds that are 120 decibels and louder. And as you get older, that number of decibels decreases where you get the threshold of pain. And it also decreases that you can even hear it. So notice how much the intensities change throughout this, but the sound levels are going up from 0 to 120, not a huge increase. The people talking at a regular voice, if you are 50 centimeters away from them, has a decibel level of 65, whereas you get to a busy street corner and you're listening to traffic, and it could be as loud as 80 decibels. If you go to a rock concert and it's loud, it's 120 decibels. It's probably actually louder than that. Some of our movie theaters are getting close to 120 decibels now, which is pretty painful for some people. And a jet plane is at 30 meters is 140 decibels. So if you think about this for a minute, 30 meters is not that huge of a distance. So if you are working at an airport, then you've got to have ear protection on, or you will have permanent hearing loss. Similarly, the glass at the airports that are near the jet near the terminals for jets have to be made in just the right shape and in just the right way so that the decibel levels on the inside of the airport don't get anywhere near 140. If we want to calculate the level of sound in decibels, we need to have a particular equation that relates intensities to decibels. Now remember, as I said, intensities are in watts per square meter, so we have to be able to change that over to decibels. So sound level has a variable called beta, and beta is equal to 10 times the log of the intensity of sound over I naught, where I naught is the minimum intensity we can hear. It is our threshold of hearing. If we use this equation that beta is equal to 10 log of I over I naught, we can figure out that in order to double the intensity, as we were talking about before, for the intensity to go to twice the intensity, the decibels only need to change by 3, and not 3 times, but 3 decibels, in addition of 3 decibels. So not a big change in decibel level for a large change in intensities. Again, because the intensity is a logarithmic scale. Okay, so this is our ear. And essentially what happens is sound waves come in the ear canal. And remember, they are pressure differences. So you're just compressing and rarefacting the air particles that are already in here. When those ear waves make it to the eardrum, it causes the eardrum to flex back and forth like the top of a timpani drum. That flexing, and some of it gets pushed back and some of it reflects back into the ear canal. The flexing of the eardrum makes it vibrate. These vibrations cause the tiny little bones here, the hammer, the anvil, and the stirrup, the 3 smallest bones in the body, to move and to hit each other in sort of a knock-on effect. This changes the pressure in the oval window at the end of the cochlea. The oval window is the area that the stirrup is actually attached to, and that is what the stirrup is vibrating, is the oval window. The cochlea is a liquid and hair-filled vessel. It looks like a snail here. It doesn't actually always have a hole in this. They've just cut a hole in it for you to see what it looks like. And it not only influences your ability to hear, but it also controls your balance. The liquid in the cochlea is what swishes back and forth, and in the semicircular canals, which swishes back and forth, which can cause you to get dizzy, as well as cause you to have motion sickness or not. The variations of vibration sensed by the hairs within the cochlea cause electrical signals to be passed through the auditory nerve, through to the auditory nerve here, and sent off to the brain. If the hairs are damaged by being forced to vibrate too much for a long period of time, or too much for short periods of time consistently for over a long period of time, then they will not grow back, they will not be repaired, and they will be permanently damaged. When that occurs, you experience hearing loss. This can occur because you listen to music too loudly, because you use power tools without proper protection, all sorts of things like that. If you were born with too few hairs or with damaged hairs, you would also have hearing loss, but you could be a candidate for a cochlear implant. A cochlear implant is essentially an electronic sensing device that takes over the job of the cochlea. So it will get the signals from the oval window that are coming in through the ear canal, and it will transmit those signals into and transfer those signals into electrical signals that can be then transmitted to your auditory nerve so that hearing is possible. These cochlear implants only work if it's just the cochlea that's damaged and not the auditory nerve or any of the other bones, but they're pretty cool and they're super fascinating. So I would suggest that you look them up. Once the signal gets to the nerves and gets to the brain, then the brain can interpret the sound and figure out what to do with it. The ear's sensitivity to sounds, however, varies with frequency. If we take a look at this picture here, these curves translate the intensity into sound levels at different frequencies. Let's take a look at the 40 line here. 40 refers to the fact that it is at 40 decibels. So let's take a look at 40 decibels. And in particular, let's take a look at this red line, this red 40 line, at a frequency of 1,000 hertz. So right here, because it crosses the line quite nicely. 40 decibels, 1,000 hertz at 40 decibels has an intensity of 10 to the negative 8 watts per square meter. In order for sound at other frequencies to sound as loud as this particular sound, 1,000 hertz sound, we can look at the red line and see what the intensity needs to be. So for example, let's compare the intensity needed to hear 100 hertz at the same level, 40 decibels, as if we heard it at 1,000 hertz at 40 decibels. Well, the 100 hertz would not be at 40 decibels now. Instead, it would be over 60 decibels. And so you would have to have an intensity of more than 10 to the negative 6th watts per square meter. Significantly higher intensity to register, for your brain to register the 100 hertz sound to be the same loudness as the 1,000 hertz sound. Similarly, if we go up in intensities, let's say we go to the 5,000 here. Now let's go about 3,000. So 3,000 hertz, the intensity has to be a little bit smaller to be heard as the same loudness as the 1,000 hertz. But then you get significantly higher than that in frequency. And again, your intensity has to go up in order for it to sound the same loudness. Notice the top line, the threshold of pain. If we are talking about decibel levels of 120, that is the threshold of pain. If you are listening to something at 50 hertz, the intensity is higher than that. If you are listening to something around, say, 4,000 hertz, the intensity is slightly lower than that, but they will sound the same to you. And again, this threshold of pain is called this because it is physically painful for you to hear sounds that are above about 120 decibels. So let's take this information and think about how the different frequencies sound like different loudnesses, even if they are played at the same decibel level. And let's take a look at other things that we listen to and note some of the values. So let's take a look at this little thermometer. I liked this picture because it puts things into perspective, including some modern implements that we use. The question is, how loud is too loud? Well, we have our silence, our threshold of hearing down here at 0 decibels. A whisper has a decibel level of about 10, leaves rustling around 20. Your running dishwasher is about 30. Moderate rainfall is 40. Heavy rainfall is 50. A normal conversation is 60. Your iPod at medium volume is at about 70. So it's typically your Your decibel level is higher than a normal conversation. Police car siren is 80, and the maximum safe exposure limit is 85 decibels. Excessive exposure to levels above that can cause headaches, nausea, and hearing damage. Even though it may not hurt yet, it's still doing damage. A hairdryer at 90 can damage your ears. Maximum iPod volume of 100 can do a lot of damage to your ears. This is why many of the iPods and other listening devices and headphones in particular have volume controls that don't let you get to maximum nowadays, especially for children. A chainsaw is at 110, the rock concert 120, fireworks can be as loud as 130, jackhammers can be as loud as 140. And so when we are looking at these, a lot of people listen to their iPods on maximum because they just want to drown out the rest of the world. Well, that's all fine and well and good, except the problem is going to be that you are going to actually damage the hair inside the cochlea, and then you are going to cause deafness. They've seen a huge increase in decrease in hearing in 20-year-olds because of the introduction of using headphones all the time, especially the little pods that stick right inside the ear canal, because then all of the reflected wave that hits the eardrum and comes back to the little bud there gets reflected back again. So there's an increased pressure already, and then you're increasing the pressure more. So it's really quite dangerous to your hearing to use the earbuds that go directly inside your ear. All right. With this information in mind, we should now be able to move on to the next video where we use the equations and this information to solve some problems. Bye for now.